Welcome everyone to The Explainer. If you're gearing up for your DPE 803 chemistry exams, and specifically looking at topic 220, well, you are in exactly the right place. You can really consider this session to be your ultimate visual toolkit, kind of like a mental map for mastering the states of matter. We're not just going to sit here and memorize dry facts today. Instead, we're going to visually unpack the incredible, invisible forces that govern our universe, from the ice clinking in your glass all the way to the plasma burning in the stars.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the states of matter, move into the kinetic theory of gases, unpack the ideal gas laws, and then look at real gases. After that, we'll explore liquids and liquid crystals, and finally, we'll wrap up with solids and plasma.
Section 1, the states of matter. We are taking a macro to micro tour. To truly understand matter for your exam, we really need to zoom way in. Look at this arrangement for a solid. The particles are packed together incredibly tight. Think of it like a seated audience in a completely sold-out theater. The particles are fixed in place because of strong cohesive forces. They literally can't move past one another. They only possess vibrational motion. They just kind of wiggle in their seats. And this restricted movement is exactly why solid substances have a definite, unyielding shape and a totally fixed volume.
Now let's contrast that with a liquid. If a solid is a seated audience, a liquid is basically a crowded dance floor. Notice how the spaces between the molecules are still pretty negligible. They're very close together, but they've broken free from that super rigid structure. The molecules now have translational motion, which means they can slide and groove past one another. Because of this, liquids keep a fixed volume, but they definitely don't have a definite shape. They just adapt to the shape of whatever container you happen to pour them into.
And this brilliantly illustrates our third state, gases. If liquids are a crowded dance floor, gases are an absolute chaotic mosh pit. The particles are spread widely apart, and the attractive forces between them, well, they're considered pretty much negligible. They are in a continuous, nonstop state of rapid, random motion in literally all possible directions. This is exactly why gases can be so easily compressed, and why they'll just wildly expand to fill whatever volume you give them.
Section 2, kinetic theory of gases, where temperature literally equals motion.
So, gases are going to make up a massive chunk of your exam. If you remember only one core rule from this part, please let it be this. The Kelvin temperature of a gas is directly proportional to the average translational kinetic energy of its molecules. What does that actually mean in plain English? It means temperature is quite literally a measure of motion. When you heat a gas, you aren't just making it, hotter in some vague, abstract sense. You are physically increasing the intensity and the speed of the molecular collisions. Heat is motion. Pure and simple.
Section 3, ideal gas laws explained. This is all about mastering P, V, T, and N.
These laws are basically your mathematical tools for dealing with pressure, volume, temperature, and moles. Let's kick things off with Robert Boyle. To avoid total cognitive overload here, just focus on this one specific relationship for now. Boyle's law states that at a constant temperature, the volume of a gas is inversely proportional to the pressure applied to it. Simply put, if you squeeze a gas, it gets smaller. Pressure goes up, volume goes down.
Now, it's really fascinating to see this inverse relationship actually playing out. Notice how adding physical mass, like placing heavy weights on a piston, increases the downward pressure. And what happens? The gas molecules are forced into a much tighter space, so the volume visibly shrinks. It's a beautiful, super intuitive physical reality that just maps perfectly to a simple equation.
Next up on the docket is Charles's law. This one shifts focus to temperature and volume, while keeping the pressure completely constant. It states that the volume of a given gas is directly proportional to its absolute temperature. Remember our kinetic theory from earlier? Heating a gas makes those particles move way faster and hit the walls a lot harder. If the pressure is allowed to stay constant, the container itself has to expand to accommodate all that crazy motion. So heat goes up, volume goes up.
Rounding out the big trio is Avogadro's law. This is where we introduce the actual amount of the gas, the moles, into our set of variables. It tells us that equal volumes of all gases at the exact same temperature and pressure contain equal numbers of molecules. It honestly doesn't matter if you're looking at super light hydrogen or really heavy carbon dioxide. If the volume, temperature, and pressure are exactly the same, your molecule count is exactly the same.
Let's see how this all builds up into the ultimate exam formula. We take Boyle's inverse relationship to pressure, Charles's direct relationship to temperature, and Avogadro's direct relationship to moles, and we just smash them all together.
The result? The general gas equation, PV equals nRT. That R right there is your ideal gas constant. If you have any quantity of an ideal gas, this one equation ties all of its physical properties together in one really neat package.
Section 4. Real gases and liquefaction. Basically what happens when gases stop behaving ideally.
Okay, major exam trap alert right here. Listen up. In chemistry, we absolutely love ideal scenarios, but we live in the real world. Let's compare the two. The ideal gas law assumes that gas molecules have essentially zero volume and zero attractive forces between them. But real gases, they're made of real matter. They have finite volume, and they absolutely have real intermolecular attractions. Now, under normal everyday conditions, they act pretty ideally. But crank up to very high pressures, where they are squeezed tight together, or drop down to very low temperatures, where they slow down, that is when those attractive forces totally take over, causing them to deviate big time from the ideal gas equation.
So just how much do they actually deviate? Well, the syllabus gives a really great example using methane gas. If methane acted perfectly ideally under a specific set of high-stress conditions, we'd expect one certain pressure. But when we run the numbers using the van der Waals equation, which actually accounts for real-world volume and attraction, we find the actual pressure is reduced by 15.65 atmospheres. Guys, that is a massive drop. It proves beyond a shadow of a doubt that intermolecular forces absolutely matter in real gases.
Section 5. Liquids and liquid crystals. Flow and order. Speaking of those intermolecular forces, let's take a look at how we measure them in a liquid. Notice the heat of vaporization in this data. That's the energy required to force that liquid into becoming a gas. Methane is way down at just 8.6 kilojoules per mole. But look at water. Water is at a staggering 40.6. This massive number basically proves that water has incredibly strong intermolecular forces, specifically hydrogen bonding, and it takes a ton of thermal energy to rip those bonds apart.
Now let me throw a question at you that completely baffled 19th century chemists. What happens when a solid melts, but only halfway? You see, we usually think of a super sharp transition, right? From a rigid solid straight to a flowing liquid. But as it turns out, nature really loves a gray area.
And the answer to that mystery is liquid crystals. Discovered back in 1888 by a guy named Frederick Reinitzer, he noticed that an organic compound called cholesterol benzoate didn't just melt normally. At 145 degrees Celsius, it turned into this milky, turbid liquid, and it didn't actually become a fully clear liquid until it hit 179 degrees. This in-between phase is honestly incredible. It flows just like a liquid, it's got viscosity and surface tension, but its molecules still maintain a strict degree of geometric order. That gives it the optical properties of a crystal.
Section 6. Solids and plasma. The absolute extremes of matter.
All right, here we are looking at the furthest extremes of matter. Over on one side, we have our solids. Their particles are rigidly locked into fixed positions by immensely strong cohesive forces, giving them incredible stability. But flip over to the total opposite extreme, and you have plasma. If you heat a gas up enough, the atoms actually lose their hold on their electrons entirely. You end up with this complex, highly conductive soup of free electrons and positive ions. Now, while it's macroscopically neutral, it responds super strongly to magnetic fields. And while it might seem totally exotic to us sitting here on Earth, plasma actually makes up roughly 99% of the visible universe. It is literally the stuff of stars.
Okay, let's synthesize all of this into actionable knowledge for your exam. Here are your high-yield facts to lock in. First, PV equals nRT is your absolute gold standard for ideal gases. Second, kinetic energy is completely mathematically tethered to Kelvin temperature. Third, remember the strict textbook definition of boiling. It is the exact moment vapor pressure perfectly equals external pressure. Fourth, know that a gas absolutely cannot liquefy above its critical temperature. I don't care how hard you squeeze it. And lastly, unlike boiling, evaporation is a surface phenomenon that occurs at literally all temperatures.
As we wrap up this explainer, I really want to leave you with this final thought as you hit the books. When we look at a glass of water, or a block of ice, or even the sun up in the sky, what we are really observing is a constant battle of energies. Is the internal energy of a substance just the chaotic kinetic energy of its moving parts? Or is the hidden potential energy, those totally invisible intramolecular forces desperately holding it all together, just as powerful? Understanding that delicate balance between motion and attraction, well, that is the true key to mastering the states of matter. Thanks so much for tuning into The Explainer. Keep these visual models in your head, and best of luck with your studies.